This lecture is going to cover the electromagnetic spectrum and how it applies to electrons and therefore how it applies to the atom. So much of the information in this lecture is rooted in advanced chemistry and physics. So if you go on to take physics, you will study more of the why and the how of this topic. But right now we're just going to go directly onto how it applies to the atom and therefore our everyday lives. So electrons. We've talked about electrons a lot up to this point, and we know that they're negative, and we know that they're found outside of the nucleus. And after learning about trends, we also know that they are in what we call energy levels. So I want you to think about a Bohr model and how when you have a Bohr model, you have this nucleus in the middle, and then around it you have these little lines are representing electrons. You have electrons outside of the nucleus, and they are in energy levels. So this first line right here, or this first ring, is an energy level. This second ring is an energy level. If we needed to go to a third one, that would be an energy level. So electrons live inside of these energy levels. Now, an interesting thing and a unique thing about electrons is that they can jump to a higher energy level. They can go from one spot to another spot. So electrons can become excited, and when they become excited, they jump to one that has more energy. However, just like us, eventually they have to drop back down to the energy level in which they came. But if you think about energy, it can't be created and it can't be destroyed, so something has to happen with this energy. So where does it go? And that energy is released as a photon. Now, you've probably heard this term photon before, and maybe it was when you were in biology and you were talking about photosynthesis, and a photon hits those chloroplasts. But most of the time, if you've heard that word photon, you're probably thinking light, and that is correct because a photon is a light particle. Now, a large controversy in science, since scientists have become curious about what light is whether it acts as a particle or if it acts as a wave. And the answer is that it kind of acts as both. So it depends on the nature of the experiment that we're performing. So light will act as both a wave and a particle. So imagine that we have a doorway. And behind that doorway is a wall. So outline, this is our doorway in red. And behind the doorway is the wall. So let's say I had a bunch of ping pong balls, which would act as particles. Okay, so they're individual bits and pieces. So just like protons, neutrons, electrons, we call them subatomic particles. Same thing we're talking about here. And if I threw these ping pong balls or the particles through the doorway, and let's say they had paint on them, where would that paint show up on the wall behind it? It would show in this area, right? It would show in the area directly behind the wall because those ping pong balls are going to go through that doorway in a straight line. I'm not going to see any ping pong balls over here if I go through that doorway and look on the other side of the wall. I'm only going to see them in that single spot. Okay? Now, what I want you to think about is waves of water. Now, let's say that I had a bunch of water instead of ping pong balls. I had a bunch of water on my side of the doorway, and I threw that water through the doorway. Where would that water go? As soon as it went through that doorway, it would just fill up any space that it could. And now think about water. It acts like a wave. So it would not pass through just like those ping pong balls. It would spread out. And light does the same thing. If you have light coming through a doorway, it doesn't just shine through that doorway. It shines in the entire room. So that is an example of light acting like a wave. And now let's go to an example of light acting as a particle. If you had a piece of metal and you shined some light on it, what would happen? That light would reflect off, correct? That's exactly what a particle would do. It's going to go in a certain direction, or it's going to reflect off of that metal. Now, what would happen if light acted like a wave in this? Think about the water. It would just spread out, correct? So in this case, light acts like a particle. So I know this is kind of an abstract idea, but as long as you kind of get the idea that light can act in various ways, you'll be okay with that objective. So now let's go to talk about different parts that you will see in a wave. So we know, think about the ocean, the wave goes up, it goes down, it comes back up, it goes down. It repeats the same motion over and over again. Same thing with light when it is acting as a wave. But there are different parts of that wave that we want to be able to identify. So we have a part called the crest. This is a crest, and this is a crest. So a crest is going to be the highest point of a wave. So make sure you're writing that down. I'm not going to write the definitions of each of these. So the crest right here is your highest point of a wave. Then we also have something called a trough. This is the trough of this wave. So if the crest was the highest point and it was up here, and this is the trough, it is the lowest point. So your trough is your lowest point of a wave. And the next thing we have is the amplitude. You've probably heard this word before. Maybe you've heard it when you're talking about speakers. An amplitude is really the height of the wave. So how tall the wave actually is. And when we're looking at that, we're looking at from here to here. So I'll do that in a color for you. Amplitude. So that is the amplitude, the height of the wave. So the next part of a wave, and this is one that we're really going to go a little bit more deeply into. I'm going to erase these for you here. The next one is a wavelength. So what does that sound like? It sounds like the length of a wave. So it is when you're looking from one point to the same point on the next wave. So if we're looking right here, it's the distance we travel from this point to the same point on the next wave, which would be right here. So we're looking at this entire thing is the wavelength of this wave. You could do it in any spot that you choose. So I could look from right here to right here. And it's going to give me the same distance, as long as you are measuring from the same point on one wave to the same point on the next. And then we have the last thing, which is frequency, and we will be going a lot more into this one as well. The frequency is the number of waves in a given time. So usually we look at per second, the number of waves that we will see per second. So that would be how many times do I go through this motion per 1 second. So in your worksheet packet, you have several pictures of an electromagnetic spectrum. It's one sheet. It's two-sided. I believe there's 4 pictures on there for you. And they all provide you the same information, but they're just written a little bit differently. So this one right here shows you the different types of waves that we can get from a photon. So as you can see, there's only a small range of these waves in this spectrum that we can actually see, and those are the visible light rays. So look how much, so right there it looks like it's a lot, but it's only this much of the electromagnetic spectrum that we can actually see with our eyes. But if you're looking at the rest of these names here, you're seeing things like radio waves, microwaves, infrared rays, ultraviolet, X-rays, gamma rays. Those are also things that, from electrons jumping energy levels, we can have. So radio waves, what do you think radio waves are? It's how we transmit information through the radio, through the television, not satellite, but through like broadcast TV. Microwaves. It's exactly what it sounds like. That is where the energy in your microwave comes from. So, also things might be familiar. X-rays. X-rays at the hospital. Gamma rays are used often in cancer treatments. They are dangerous to cells, which is why they're used to kill cancer cells. But what you can see here is this one, this spectrum here goes by the wavelength. So we have those with longer waves down here, this is in meters. So one radio wave, is 1 times 10 to the second meters. But one gamma ray is 1 times 10 to the negative 13th meters. So you can see there's a large range of the distance in one wavelength for the different types of waves. We're going to come back to this slide here because we're going to be using this once we figure out how to find the different values of the wavelengths of waves. So there are some equations and there are some constants that we are going to be seeing. Now, just like with density, you will be given this sheet with this information. But you will not be given all of it, so I want to be sure that we're clear on what you're going to actually be given. So the first thing is we have a constant that is c, and that is the speed of light. Through experimentation, we have found that the speed of light is 3.0 times 10 to the 8th meters per second, which means that light will travel 3.0 times 10 to the 8th meters in 1 second. So the things that you will be given on your equation sheet is you'll be given this, and you will also be given that is the value of c. I will not tell you, I'm going to put that in red, things that you will not get, is that represents the speed of light. So you need to know that the speed of light matches up with this value. So the next thing we have is this thing called Planck's constant. So this is a constant that is used in equations. It does not change. A man named Planck discovered this. You will be given this, and you will be given that it's h. You will not be given that it is called Planck's constant. It's important to remember that these do have units. So the units on the speed of light are meters per second. The unit on Planck's constants are joules times seconds. So there could be a little dot in there. Joules times seconds. So the next thing we have is energy. Energy is represented by a capital E, and it should be written in the units of joules. I will not tell you any of this. Okay, there's no value here, there's no constant here, so you will not be given that information. But just remember that E is energy. That should be easy enough, and remember that it is given in joules. The next thing is that you have V equals the frequency. Your units are hertz, which is the same as the units of 1 over seconds. So this part right here, the 1/seconds, will come into play when we start doing the problems and when you need units to cancel. But when you're given to a problem, a lot of the times it will be written as hertz. So you want to remember that hertz is the same thing as 1/seconds. The next is the symbol for wavelength, which is a symbol lambda. Also will not be given this. But your wavelength should always be in meters. So that is so your units cancel. So if you're not given a wavelength in meters, if you're given the wavelength in kilometers or millimeters, you have to convert. That comes back to stuff that you did in Unit 1 with doing metric conversions. You will be given this equation right here. C equals lambda times V. That is your speed of light equals your wavelength times your frequency. You will also be given this equation. The energy equals Planck's constant times your frequency. So you do not have to memorize the things highlighted in yellow. You should know the things highlighted in, or you should know the things underlined in red on your own. The things in yellow will be provided for you. So the nanometer. We've seen this in metric conversions. I told you you did not need to know it when you did them then. You do need to know it now. So 1 nanometer equals 1.0 times 10 to the -9th meters. So if you are given a problem in nanometers, remember I said your length needs to be in meters. So you are going to have to convert. So how are you going to do that? You're going to use dimensional analysis. So we have 500 nanometers. For nanometers to cancel, it needs to be on the bottom. 1.0 times 10 to the -9th meters should give me 5.0 times 10 to the -7th meters. So plug that in, nanometers cancel, you're left with meters. So then we're going to do a few problems here. Make sure that you have your calculator for these because we are going to be plugging them in, and I want to make sure that you're plugging them in correctly. So some practice problems. Make sure you have your calculator. If you do not have your calculator, do not watch the rest of this video until you have it. So some practice problems. The wavelength of a wave is 2.0 times 10 to the -5th meters. What is the frequency of this wave? So we have two equations. Remember, the C equals... So I'm just going to give you that. I'm not giving you what the symbols mean. So you need to be able to recognize which equation you're going to use. So the wavelength is given here. And we are looking for the frequency. So we have wavelength and we have frequency. Now, I have wavelength in this equation, and I have frequency in this one, and I have frequency in this one. So which equation do I want to use? I want to use this one right here. Now, C is a constant. So 3.0 times 10 to the 8th units, meters per second equals. So this first one, the purple here, this is my wavelength. 2.0 times 10 to the -5th meters. And I'm multiplying that by my frequency. Now, this is just some simple algebra here. Multiplied by it on this side, so I need to divide. So divide each side by 2.0 times 10 to the -5th meters. Now my units of meters are going to cancel. And what I'm going to be left with is 1.499 times 10 to the 13th 1/seconds. Because if you look here, see how I got rid of my units of meters on top, but I don't have seconds on the bottom? If I get rid of a unit and I'm left with nothing, that's going to revert to a 1. So I'm left with 1 over seconds. If you remember what I said before, that's the same thing as hertz. Now, if you did not get the number that I got, maybe you got this part, but your exponent was off, make sure that you are using that E button that I told you about in the calculator. It's very important because you're going to be working with a lot of numbers that have very high exponents, whether it's a negative exponent or whether it's a positive exponent. They're going to be large numbers, and you do not want to write that number out every time. The reason we write it in scientific notation is so you do not add extra zeros or take off zeros. So you want to make sure that you're really using your calculator. So our next problem, the frequency of a wave is 3.5 times 10 to the 15th hertz. What is the wavelength? So our equations again. Now, one of your keys is if it doesn't say anything about energy, you're probably not using this equation, because this equation has energy, this one does not. So the frequency is what we're given. So that is right here, and we are searching for the wavelength. We know what C is. C is 3.0 times 10 to the 8th meters per second. This is what we're searching for. Wavelength times my frequency. Watch how I'm going to write the frequency when I put it in this problem. I'm going to write it as 1 over seconds. Okay. So now just back to some simple algebra stuff you did in Algebra 1. To get this by itself, I need to divide on each side. 3.5 times 10 to the 15th, 1 over seconds. And then once we do that math, we'll first look at your units. Your units of seconds are going to cancel. So we are left with meters. And I get 8.566 times 10 to the -8th meters. Now remember, a lot of the times if you type it in the calculator wrong, you will get this part correct. However, this part right here, you will not. And that part is important as well. It has a huge impact on what we are looking at and what types of waves we are dealing with. So make sure that you are using your calculator. Make sure that you are using the parentheses, and make sure you are using the E instead of times 10 caret exponent. Okay? If you are confused or you don't remember how to do the E part, please see me. Do not try and guess. Please see me so we can get that handled. So here's another problem for you. Determine the energy of a wave with a frequency of 5.76 times 10 to the 14th hertz. So remember what I said. Anytime you see energy, probably using this equation first. Okay, so that should give you a hint that you are going to have to use this equation at some point. So we're looking for the energy, and we are given the frequency. So we know this part. We're looking for this. And if you remember back to that constants page, this is Planck's constant, which is a number that is always the same. So E equals, Planck's constant is 6.626 times 10 to the -34th joules times seconds. And multiplying that by 5.76 times 10 to the 14th. I'm going to write this as 1 over seconds again. Because now look, seconds are going to cancel. And now we are going to be left with joules. And if you remember, joules was the value or the unit that we want to be left with for energy. So now you just got to multiply, and you should end up with 3.82 times 10 to the negative 19th joules. Make sure that you're typing that in your calculator and getting that as well. So pause it if you have not done that math yet. Last problem. What is the energy of a wave with a wavelength of 3.9 times 10 to the negative 9th meters? So I said anytime you see energy, you know you're going to use this equation at one point or another. But this problem gives us wavelength. This equation requires frequency. So what do we do now? Use your other equation. Because now I know what my speed of light is. I know what my wavelength is because it was given in the problem. Now I can solve for the frequency. Once I solve for the frequency, then I can use this equation. So this is a two-step problem here. Do not be afraid to have to use both equations. So we're going to use 3.0 times 10 to the 8th meters per second. So we're using this equation first, equals my wavelength, which is 3.9 times 10 to the negative 9th. Oh. Times 10 to the negative 9th meters. Make sure you know this is a 9. And we're multiplying that by our frequency, which we do not know. So we're going to solve on both sides. We got to divide. Negative 9th meters. My units of meters are going to be canceled, so I'm going to be left with units of 1 over seconds, which is the same thing as hertz. So when I do that math, I end up with 7.69 times 10 to the 16th. So that is your frequency, but that's not what I'm asking for in the problem. What we're being asked for in the problem is the energy. So we have to do one more step. So if you do not have this yet, pause it and get this stuff written down and do this math because I'm going to erase the things on this screen. So I'm going to leave this value down here because we do need this. So now we're going to use this equation, the energy equation, because that's what we're really looking for. So E equals 6.626 times 10 to the negative 34th. Where did I get that number? Right, it's a constant. Joules times seconds. And we're multiplying that by 7.69 times 10 to the 16th. 1 over seconds. That number came from here. So now our units, get rid of those. Seconds cancel. We are left with joules, which is what we want because we are solving for energy. And when we plug that in, we get 5.09 times 10 to the negative 17th joules. So you do have a lot of problems that look like these. It just is algebra. Do not be scared by the numbers. Make sure that you are comfortable plugging them into the equations or into your calculator, and make sure that you are familiar with the algebra. Do not just guess. Make sure you're multiplying when you should be. Make sure you are dividing when you should be. And I want to go back to this problem right here where we're looking for the wavelength. If you look at your last objective of this quiz, it says something about being able to use data to interpret information. So something additional I could ask you about this was, what type of wave are we looking at here? And now you're probably thinking, how do I know that? Well, if we have the wavelength, we can use that electromagnetic spectrum that we looked at a few slides ago to determine what type of wave it is. So we're looking at 8.566 times 10 to the negative 8th. This is where your exponents really, really come into play and are very important because they're going to help you determine what this is. So if we go back, something times 10 to the negative 8th. So we're looking at our wavelength here. So along this line, you should be able to find that. So times 10 to the negative 8th is going to be right about here, which means we're looking at something that is in the ultraviolet ray. So if I were to ask you what type of wave that was that had a wavelength of 8.566 times 10 to the negative 8th meters, you could tell me that that would be an ultraviolet wave. Maybe you get something that's 10 times, or something times 10 to the second. Those would be radio waves. Maybe I give you something and I want to know if it's in nanometers. That would be converting back and forth with those nanometers. Okay, so be familiar with this. I will also give you a spectrum that looks just like this on your quiz as well, so you do not have to remember which ones are where. But do be familiar with actually reading these values and applying them. Right, that's all for this one. Good luck.